bubbles.
All right. Hello, everyone. Thanks a lot for an awesome introduction. And I would like also to thank the organizers for the opportunity to present our work today. Now, yeah, okay. So this work wouldn't have been possible without these brilliant and amazing people. So there is Yusra and Laurent from the University of Arkansas, and the team of experimentalists, the group of Nagi Valanur. And personally, from me, many thanks to the HPC team at University of Arkansas, who are very patient and are always super responsive. Now, today, everything I'm going to be talking about concerns thin film structures of PZT that are buffered with STO layers, so that at the interfaces we have incomplete screening of the bound charges. And in this case, the polar structure becomes sort of non-trivial. The first prediction of this phenomena was given by Igor Kornev and from the group of Laurent Belège in 2004, where they shown the formation of sort of what they call nanostripe domains, which now is realized have the vortex tube topology. And also, in the same paper, they've presented the first evidence of what we call now the bubble domains, which appeared when a bias electric field was applied on those nanostripes. The dipoles were partially switching, thereby disconnecting the nanostripes and leading to this spherical domain formations. And eventually, the bubbles, upon applying further field, it was showing that the bubbles would also eventually disappear, leading to a homogeneously polarized state. Now, this picture allows to actually understand also the structure of the bubbles really nicely. So we start with this nanostripe state, which is reminiscent of the stripe domains, with the only difference that instead of the domain walls separating up and down domains, we have those vortex tubes. And then upon applying electric field, what happens is that the stripe domains break, as you can see here, the upper inset, and the tubes reconnect, thereby forming those those circular vortex structures. And eventually, when the breaking reaches the point that the stripes are no longer visible, you get those donut-shaped vortex-like structures, which we call bubbles. Now, it was recently realized that ferroelectric nanostructures with incomplete screening can be actually mapped to the to incompressible liquids. A very nice idea put forward by Professor Lukyanchuk. And here we realize as well that this type of structure, as well as the Hopfion, can be linked to some hydrodynamical structures. For instance, here you see what is called the vortex ring or spherical vortex. Structures that commonly appear in gases and fluids. One example is for instance, the streams of air created by a helicopter or the falling dandelion. Now, with respect to topology, it's not a fully settled question, but there are a lot of similarities between bubble domains and magnetic skyrmions. So what I showed you before, the mechanism of formation of bubbles, essentially tells us that bubbles are intrinsically related to those nanostripes, exactly in the same way as magnetic skyrmions are linked to the spin spiral structures, which are also can be seen as some sort of stripe domains. Now, and magnetic skyrmions as well, they appear, they form upon application of an out-of-plane magnetic field. So here the analogy holds very well. Now, at the same time, if we really look at the topology, we would realize that it's not quite the skyrmion because of many reasons. I hope soon we'll have this short review published where we explore this idea a little bit more. But the thing is that for now, well, let's call it skyrmion because at the poles of the structure, at the upper and lower interface, you see the appearance of the so-called nail skyrmions or hedgehog skyrmions, which looks very much like the Nagi's haircut over here. And now, having finished with some basic introduction on the structure, let's take a look into the physics of the formation of bubble domains. Now, this simple picture is very clear, but still there is a question: why the switching happens in this way and not in any other way? The stripes could have shrinked. Some other patterns could have formed. So why this switching path? And the answer to this question was given or at least we tried to give an answer to this question in this paper from 2020. Yusra had this idea that essentially because of this quasi-two local symmetry, because of the compressive strain, the dipoles are constrained sort of to be out of plane, which hence the nanostripe patterns. And because of this strong depolarizing field that sort of governs the width of the domains, that fixes it to a certain wavelength, we should fall in the scenario of the so-called constrained order parameter thermodynamics, which actually turned out to be true, this idea. And we were able to recover this classical bell-shaped phase diagram, where you have spinodal regions, spinodal decomposition regions, and nucleation regions. So even out of equilibrium, the system sort of evolves as if polarization was fixed. And the value of this fixed polarization, of course, depends on the external bias that is applied. Now, what's nice about this this probing is that it's sort of opens the way to a very big world of self-assembly and pattern formation. Similar structures are seen in many different types of systems. For instance, cloud formations, the sand dunes, the coloring of animal skins, chemical reactions. So here also the structure of alloys. And another nice thing about it is that essentially this very complex phenomena, you can sort of squeeze it in a very simple model that that is analytically traceable and that a priori doesn't know anything about bubbles, but is proving to be very useful. Now, more on the physics of bubble domains you can find in those papers. We explored this idea, but also the influence of depolarizing field and different parameters on the bubble properties. So let's recap a bit. So with respect to the structure and topology, we saw that bubble domains are sort of spherical vortices, and they share a lot of similarities with the magnetic skyrmions. And in terms of physics, what I would like us to keep in mind is that bubbles are intrinsically related to the nanostripes or polar vortices, and either in the disordered glassy realization, like labyrinths here, or in the crystalline realization, like nanostripes. And essentially, it's the value of polarization that determines whether your structure is going to be bubble-like or labyrinth-like. Now, with respect to the applications, bubbles were shown to have many interesting functional properties. For instance, high responses to external fields, tunable conductivity. They can be written and erased with electric fields and pressure. Now, what about the motion? I hope I convinced you that bubbles share many similarities with spin skyrmions, and those can be moved, which led to this concept of the racetrack memory. But also, there's this link to the nanostripes and labyrinths, and as we saw previously, those also exhibit dynamics. So supposedly, bubbles should move as well. Now, we would like to explore this idea at room temperature, and particularly with, and we have this, we have many actually handles to tune the properties of bubbles. But here, what I would like to explore is essentially the applied bias and the screening. So the screening here is some sort of effective parameter. The more the screening, the more this beta parameter is, the better the screening. So beta equal 1 sort of translates into perfect screening conditions. Now, what we want to do before any motion is that we want to get rid of this hexagonal lattice structure, because if you want to move individual bubbles, you need space for that. So we would like to be in a limit of dilute bubble lattice, where we don't have much bubbles. And if you take a look at the phase diagram here, you can see that you can achieve it with the field and with the screening. And this graph here shows you the density of bubbles. But what I find extremely interesting is that the transition line between bubbles and the homogeneously polarized state features at a critical point, which is highlighted here with the blue dot. Surprisingly, you can recover it with the model that I was talking to you about before. But why is it there, and what kind of implications does it have? So for sort of poor screening conditions, we have the continuous type of transition between bubbles and homogeneously polarized state. And for better screening conditions, we have this first order transition, this continuous transition that yields sort of many metastable states. But now, for now, let's look what does it translate into in terms of bubbles. So in reality, this part of the phase diagram we have explored already. And what it leads to is essentially some sort of static metastable states where you have different density of bubble domains. And this yields, for instance, hysteretic behavior at the transition, so which perfectly falls in the picture of the nucleation. But now, what about the continuous transition? So in this case, the hysteresis of the density disappears. And we're wondering what happened to the metastable states. Bubble domains are domains after all, so once they're there, you expect them to be there. Now, interestingly, what happens in the vicinity of this transition line is that we see some sort of liquid or gas behavior. Whenever bubbles start to disappear, they also start to move and dynamically appear, disappear. So it resembles some sort of gas of excitations, which actually allows to recover this continuous transition between bubbles and the homogeneously polarized state. Interestingly, we did some recent probings and to see whether we can have any meaningful phonons in this kind of state. And as a matter of fact, you can sort of discern some spectral lines, quite broad, but still, which put some questions about the nature of the state. But this I would leave aside for now and focus on the underlying energy landscape. So the basic idea is that within the bubble states, whenever you have some holes, whenever some bubbles disappear, you can sort of reorganize your lattice in many ways. Those defects can appear here, there. So you have a multitude of states and a very extensive configurational space. Now, each of those states in the first order transition region, they were metastable. So this suggests some sort of hierarchical energy landscape picture, like shown here. So the coordinates here is the energy versus the number of bubbles. And we have this sort of global basin with a global minima that corresponds to the equilibrium number of bubbles. But also you can remove and add bubbles, which would lead to adjacent metastable minima. Now, not only that, but also the rearrangement of the bubble structure in space, like shown here, also features some sort of energy landscape, which here it's shown to be not flat, because there's always some disorder, some defects. So different positions in the crystal would yield different energies. And what we wanted to do is to sort of explore this picture, because those hierarchical energy landscapes, they're also interesting from the point of view of the glass physics. This is sort of the seminal idea that the glass behavior stems from this kind of energy landscapes. So we did some calculations using the nudged elastic band method. And here you show the results under different bias fields for the change of energy with respect to the number of bubbles. And as you can see here, indeed, the picture sort of proves to be what we thought it was. Now, to create or erase bubbles, you need to overcome a certain barrier. But also you have this sort of global minima that defines the equilibrium number of bubbles. Another thing that I would like to point your attention to is the height of the barrier here, which is sort of translates into the topological protection barrier, if you believe this concept. And in this particular case, it's sort of comparable to what you would see in case of magnetic skyrmions. Now, what about the real space picture? What about the Pyro's potential? We saw those hoppings in the animation that I showed you. There were those hoppings where the bubbles would disappear, appear in another place, but also would move, continuously move from one place to another. So to probe those barriers, we have this part of the energy landscape. We have also performed the NAB simulations at low temperature. And in those simulations, we were starting with one single bubble in one place. And this was the initial state. And the final state was either, let's say, some distance away from this initial state. But in both cases, there was a single bubble. So we start with a single bubble here, and we end up with a single bubble here. And the distance between those two is plotted on this x-axis here. And as you can see, to sort of move a bubble a little bit by one radius, the barrier is extremely small. But then also you have this sort of hopping, right? So you start with a bubble here, and then you end up with a bubble here. Our simulations show that there are no intermediate states, so the bubble doesn't really continuously move, which I guess leads to some sort of perhaps not optimal path, because the optimal path would be to follow sort of this this pattern, but there must be some value that actually makes those hopping paths sort of metastable, if you see what I mean. And here you see the height of the energy barrier depending on the hopping distance, which sort of increases with the distance. Now, we saw spontaneous motion of those bubbles and spontaneous hopping, as well as creation and annihilation. But what about doing it on purpose, artificially? Now, obviously for this, and we envision sort of from what I explained before, we envision two types of possibilities. One possibility is sort of drag, which can be, I guess, accomplished with a PFM tip. And the second possibility, which is sort of under question for now, can we have a single bubble state like this, then apply a local electric field somewhere far away, and have this bubble erased, whereas the new bubble will be created under the chip. So for this, of course, we have to be within the first order transition region. And we did some simulations showing that, for instance, if you apply a local electric field in the vicinity of the bubble, what will happen is that the bubble will elongate and sort of move to the new position. And also what we saw is that if you apply a very strong field far away, what will happen is that you will have sort of bubble gradually transfer from one position to another. Now, I would like to those are molecular dynamics simulations, and I would like to point your attention that there is no intermediate state where there are, let's say, both bubbles are created. It's always, let's say, the middle state here is that half a bubble is in one spot and Another half bubble is in another spot. Nagi and Vivasha and Peggy, they got really excited by this idea and they tried to do the experiments. And what they saw, so in their case, it's sort of tricky. They cannot. It's very hard. It's very challenging to control the conditions to make this process work optimally. But what they managed to see, for instance, here you see that we have some sort of bubble state, and then they apply a strong electric field right over here. And well, surprisingly, what they saw is that 2 bubbles disappeared and 1 big bubble appeared, which sort of proves the point in my mind. And with this, I would like to end my talk. So in summary, we have demonstrated the control of bubble density at room temperature using the screening and electric field parameters, and also explored the energy landscape governing the physics of the bubble states. What was found is that depending on the character of the phase transition between the bubble and homogeneously polarized states, one can have either a hysteretic behavior, which allows you to have many different metastable bubble configurations, or in case of the continuous transition, we obtain this dynamical state, the excitation of bubbles, which is very much similar to those domain polar liquids that were discussed previously during this conference. And I believe that we have preliminary experimental demonstration of this bubble teleportation phenomenon. And with this, I would like to thank you. And I'll take the questions.
Thank you very much. The question is, loads of questions. All right, I'll start with the first one.
Thank you for the talk. I think it's possible by finding that in order to move power from one position to another position, you have to overcome the variable. Is there something in the local structure? Are you simulating alloy or geometry? So what makes that variable be there?
Yeah, I mean, it doesn't matter if it's so like we see it both in the alloy and in the homogeneous system. The difference between those two is the energy landscape over here. The alloy would look like so, and in case of a homogeneous system, it will be just flat. The barrier height will be the same everywhere, and the position of the minima would be the same everywhere. And those barriers, it's like the motion of the domain wall. It's essentially associated with the energy that is needed to switch the dipole, but not one dipole in this case. So you have a small, let's say, updomain, and to move it a little bit, you have to switch those dipoles that are surrounding the bubble, and that's what produces the barrier.
Thank you very much. I have a question about size of the bubble and order of this area. And yes,
so experimentally or from simulations? Yeah. Yes.
How big would be the real system?
Yeah, I mean, so of course, with respect to the size of the bubbles, it depends on many different things. For instance, the thickness of the film, the value of the compressive strain. It can be sort of managed, the size of the bubble. But it's important to see the difference between a bubble and cylindrical domain. So a bubble is a very tiny cylindrical domain, if you want, which actually allows all those things. It's because it's small that you can have those liquid states. It's because it's small that you can yeah, like around like 4 nanometers. Like in our simulations, it's smaller than that, but in our simulations, it's about 2 nanometers. But experimentally, they see something around 4, and And actually experimentally what they see is also that when they, let's say, create a cylindrical domain, it will sort of with time, it will shrink and stabilize at some very small size. If the conditions are good. So for the barrier height, of course, it depends on the size of the bubble. Now, in our case, I must warn you, effective Hamiltonian might overestimate the barriers. But it sort of looks that, for instance, to continuously move the bubble, you need electric fields that are about 10% of the coercive field. And to teleport the bubbles, you need something that is much stronger, that is at the order of magnitude, actually higher than the coercive field.
Okay, thank you. Very nice talk. I enjoyed it. And two questions. All time. So this is landscape you have here.
Yes.
What a position we take from the and you couldn't take the entire height. And also, we use strategy instead of the application.
Yes. Yeah, I mean, that would be fantastic.
Because you describe as fidelity compositions. And so that means the atomic mechanism they have remove individual atoms, right? So you have the program, you have to remove the whole collapse, you have individual atoms moving the capture and field.
No.
Okay.
That's the yeah. I see what you mean, but it's not the there's no diffusion. It's the analogy. So if you want, you can describe this diffusion process with the Ising spin model, and the flipping would mean something actually moving, right? But in our case, the same spin model it just means that the dipoles are flipping, but nothing is physically moving. There's no mass transfer.
I mean, the spin is a transfer.
Yes, correct. Yeah.
If you think about spin transfer.
Yes,
not
correct.
atom transfer.
Yes. There is a dipole transfer if you want.
But still, individual one be connect together.
Yes.
Okay.
Correct.
Thank you.
I was wondering in the populations where the report actually the energy landscape on the
Yes.
you know what would be the maximum distance which you will be able to the bubble, and if you're running closer to the bubble, the report faster on the other time scale that is changing the distance from the bubble.
That's a fantastic question. So I mean, bottom line is that it happens because sort of the system has fixed polarization. That's the bottom line, right? So if the energy barriers are well tuned, you have some conditions to be met, right? So now it's a good question. What part of the sample would know that another part of the sample is switched, and how fast it will happen? I'm not sure. I'm not sure our models can deal with that. Now, with respect to the speed of the transfer, it doesn't depend that much on the distance, but rather on the magnitude of the field. The bigger the field, the faster it will flip.
So I wonder if you have considered pushing a formal analogy, some sort of Schrödinger equation. So what I see is that strain, you can create the deformation potential out of the strain of the bubble. And when you apply the field with the tip, you're doing that. So basically transferring electric fields to deformation fields. And somehow we're getting a double weight of the bubble. So I wonder, so it seems that your argument is that there is something to that barrier.
Yes.
So I wonder if to your formal equations, if you can push that analogy.
Yes, I see the question, and actually, I mean, this is sort of was the point of the talk of Suyash yesterday. So he was essentially, I think, saying that those guys, Labyrinthes or stripes or whatever, are waves. and the liquid state is the superposition of waves, right? And also the now we know that skyrmions, for instance, magnetic skyrmions, it's not a new idea. It's been known for a while. Can be seen as also as a superposition of spin spiral states. You need 3 spirals, right? So I guess in the case of bubbles, it will also be the same. And here we strangely, so where's the slide? We do see some sort of signatures of wave-like behavior. I mean, in this type of dynamics, I would expect spectral mass, right? But we do see some sort of lines which indicates and softening of the phonons, which sort of indicates to me that this picture is not fully absurd. But yeah, to get to some equation on that, it's yeah, it's a very interesting idea, but I don't know where to start. Sure.
All right, let's take Sergei again. It's going to be ready for coffee break, right?
Yeah, of course. Thanks a lot.
All right, let's start. Microphone on.
Okay.
What are you doing? What?